Hello everyone, welcome to new class. Today's class is about the stability analysis in control systems. So, the term stability refers to the stable working condition of a control system. And every working system is designed to be stable. In a stable system, the response or output is predictable, finite, and stable for a given input. And before going to the stability analysis, let us know about the different definitions of the stability. First one is a system is stable if its output is bounded or finite for any bounded input. Second one, a system is asymptotically stable if in the absence of the input the output tends towards zero irrespective of initial conditions. Third one, a system is stable if for a bounded disturbing input signal the output vanishes ultimately as t approaches infinity. Fourth one, a system is unstable if for a bounded disturbing input signal the output is of infinite amplitude or oscillatory. Fifth one, for a bounded input signal, if the output has constant amplitude oscillations, then the system may be stable or unstable under some limited constraints. Such a system is called limitedly stable. Sixth one, if a system output is stable for all variations of its parameters, then the system is called absolutely stable system. Then the seventh one is if a system output is stable for a limited range of variations of its parameters, the system is called conditionally stable system. So these are some definitions of the stability. Next is response of a system. Let the closed loop transfer function is equal to C of S divided by R of S equal to M of S. Then the response in S domain is C of S equal to M of S into R of S. The response in time domain is C of T is equal to Laplace inverse of C of S. And let R of T is equal to Laplace inverse of R of S. Then for an impulse input, R of t is equal to delta of t. Therefore, R of s equal to Laplace transform of L of delta of t is equal to 1. Then the impulse response of the system is the Laplace inverse of C of s equal to inverse Laplace transform of M of s into R of s. That is C of s is M of s into R of s. And we get R of s is 1, so we get L inverse of M of s, and that is equal to M of t. Hence, the impulse response of a system is the inverse Laplace transform of the system transfer function, where M of s is C of s divided by R of s. And the advantage of impulse response is that the knowledge of impulse response can be used to determine the output of a system for any arbitrary input. Next is location of roots on the S-plane for stability. The closed loop transfer function M of S can be expressed as a ratio of two polynomials in S. The denominator polynomial of the closed loop transfer function is called characteristic equation. So denominator polynomial is characteristic equation, and the roots of this characteristic equation are poles of closed loop transfer function. So M of S can be expressed as B0 S raised to M plus B1 S raised to M minus 1 plus etc. plus Bm minus 1 S plus Bm divided by A0 S raised to N plus A1 S raised to N minus 1 plus etc. plus An minus 1 S plus An, and that is equal to S plus Z1 into s plus z2 into etc. s plus zm divided by s plus p1 into s plus p2 into etc. s plus pn. The roots of the numerator polynomial z1, z2, etc. zn are called the zeros, and the roots of the denominator polynomial p1, p2, etc. pn are called the poles. The denominator polynomial is the characteristic equation. Denominator polynomial is the characteristic equation. So the poles are roots of the characteristic equation. And by partial fraction we can write m of s equal to a1 divided by s plus p1 plus a2 divided by s plus p2 plus etc. plus an divided by s plus pn. And the poles p1, p2, etc. pn may be at origin or lying on imaginary axis or lying on right or left half of the s-plane. So the impulse response is given by inverse Laplace transform of m of s, and the inverse Laplace transform of each term of m of s depends on the location of the poles. Let us find the impulse response of various terms of m of s. So first one is the transfer function and location of the roots. So let m of s equal to a divided by s plus a. So here we get s equal to minus a, that is root on the negative real axis, and that we can locate like this. So this is sigma and this is j omega. So s equal to minus a, so we can locate here. So the root is on the negative real axis, and the response will be m of t. So m of t is the response. M of t is equal to L inverse of a divided by s plus a, and we get a into e raised to minus at. So it is exponentially decaying. It is e raised to minus at. So the response is exponentially decaying. This is t and this is m of t, and this is a. So this is the response of a divided by s plus a. Second one, let m of s equal to a divided by s minus a. So here s is equal to a. That means the root is on the positive real axis. That is, we can locate the root like this. This is sigma j omega, and this is the root, that is s equal to a on the positive real axis, and its response is m of t equal to L inverse of this one, and we get a into e raised to at. So it is exponentially increasing. This is t and this is m of t. So the response is exponentially increasing. Next is m of s equal to a divided by s plus a plus jb plus a divided by s plus a minus jb. So here the roots are complex conjugate, and s is equal to minus a minus jb. Here a minus a plus jb. So the complex conjugate roots on left half of s plane, that is, this is sigma j omega minus a minus jb, and one is minus a plus jb. So minus a minus jb. So let this be minus plus jb, and this is minus jb. So a. So one is here and other is here. That is, this is a minus jb, and this is minus a plus jb. So this is minus a. And its response. So the response m of t is equal to L inverse of this one, and we get a e raised to minus a plus jb t plus a e raised to minus a minus jb into t. Or we can write it as 2a e raised to minus at cos bt. And the response is, this is t, m of t. The response is damped sinusoidal, that is damped oscillatory, and this can be written as cos bt, we can write as sin bt plus 90. So the response is like this, that is the response is damped sinusoidal. Next is m of s equal to a divided by s minus a plus jb, then plus a divided by s minus a minus jb. So here the roots are on the right half of s plane and complex conjugate. So we can locate the roots like this: sigma, this is j omega, here s equal to a minus jb, here s equal to a plus jb. So this is a and it plus jb, this is minus jb. So the roots are like this. And the response is m of t. M of t is equal to L inverse of this one, and we get 2a e raised to at cos bt, or we can write it 2a e raised to at sin bt plus 90. And the response is exponentially increasing sinusoidal. So we can locate the response. This is t, m of t, and this is the response. So the response is exponentially increasing. That is, the amplitude of oscillations exponentially increases with time. Next is m of s equal to a divided by s plus jb plus a divided by s minus jb. That is s equal to jb, here minus jb, here s equal to plus jb. That is the single pair of roots on imaginary axis. That is, we can locate the roots. This is sigma j omega. So s equal to minus jb means it is here minus jb. Then s equal to plus jb means here. So single pair of roots on the imaginary axis. And response is m of t is equal to L inverse of this one, and that is equal to a into e raised to minus jb plus a e raised to plus jb. And we get the response as t, this is m of t. So response is oscillatory like this. because here we get this as 2a sine bt plus 90. So the response is oscillatory if the roots are on the imaginary axis. That is single pair of roots on the imaginary axis. And another case is double pair of roots on the imaginary axis. That is, if m of s equal to a divided by s plus jb the whole square plus a divided by s minus jb the whole square. So here it means that the imaginary roots are double pair. That is, here s equal to minus jb, again minus jb, that is double. Here also s equal to plus jb, it is double. So we can locate like this, sigma j omega. So double pair of roots, here double pair of roots, this is jb, this is minus jb, and the response is m of t is equal to a into t e raised to minus jb plus a into t e raised to plus jb, and the response is like this, that is t m of t. So this response is linearly increasing sinusoidal, that is the amplitude of oscillations linearly increases with time. Next is m of s equal to a divided by s, that is single root at origin, s equal to 0, that is we can locate sigma j omega, this is the root, so single root at origin, and here the response is m of t is equal to L inverse of a divided by s, that is equal to a. So m of t is, that is the response is constant, it is a, and another is m of s equal to a divided by s square. So that means there are double root at origin, so we can locate the root like this, sigma, this is j omega, so double root at origin, and the response m of t is equal to a into t. So we get m of t as, the response is linearly increasing with time. So this is the response. And note that the poles are denoted by this cross and zeros are denoted by 0. So poles are denoted by these crosses and zeros by a small 0. And in summary, the stability of the system depending on the location of the roots of characteristic equation can be write like this, that is, if all the roots of the characteristic equation are negative, has negative real parts, then the system is stable. So if all the roots of the characteristic equation has negative real parts, then the system is stable. And if any roots of characteristic equation has positive real part, or if there is a repeated root on the imaginary axis, or repeated root on the imaginary axis, then the system is unstable. Then third one is, if the condition 1 is satisfied except for the presence of one or more non-repeated roots on the imaginary axis, then the system is limitedly or marginally stable. So condition 1 and one or more non-repeated roots on the imaginary axis, then the system is limitedly or marginally stable. So first one is, if the roots of the characteristic equation have negative real parts, then the system is stable, and if any of the roots of the characteristic equation has positive real part, or if there is a repeated root on the imaginary axis, then the system is unstable. And the third one is, if the condition 1 is satisfied except for the presence of one or more non-repeated roots on the imaginary axis, then the system is limitedly or marginally stable. So that is about the stability of a system. And in the next classes, let us study about different stability analysis like root Hurwitz criterion, then root locus, etc. So thank you for watching the class. If you like the classes, please like, share and subscribe my channel.